Welcome in. Our objective for this video is to determine the correct chemical formula for ionic compounds. Recall that we said ionic compounds form between metals and nonmetals, or cations and anions. And when we form ionic compounds, we need to do that with our charges in mind. Our final compound has to have an overall charge of 0. It must be neutral. We can use this to set up a couple of nice math equations. The total positive charge has to be equal to the total negative charge in terms of their absolute value or their magnitude. Or in other words, the total positive charge and the total negative charge have to add up to 0. Well, we have some good news then. If we know what cations and anions we have, we can use their charges to predict exactly what the chemical formulas must be. Our plan is straightforward. We need to make sure the charge is neutral. And we need to make sure we have the simplest ratio possible. We'll introduce a few different plans on how to do this. Here is one method. We can try to visualize what's going on. We have a lot of positive cations and we have a lot of negative anions. We want to try to scoop up enough of each of them to make sure that we have a nice neutral overall compound. Our atoms are never going to exist in isolation. If you're thinking about, for example, aluminum and oxygen, you're never going to have just a single aluminum atom. There's going to be plenty of them to go around. Here I've drawn out 3 of those aluminum atoms. And likewise, I've drawn out 3 oxygen atoms. We can predict exactly the charge on aluminum and exactly the charge on oxygen using the periodic table. So now we just need to decide how many of each of these are required to give us a nice neutral compound. We can try to grab just one of each, but we can immediately see that this is not going to work. 3 positives and 2 negatives is not going to be good enough. We can add some more negatives by grabbing more oxygens, but this still doesn't quite work. We have 3 positives and 4 negatives. We can grab maybe 2 of each. This is the same problem as 1 of each. We can try to grab maybe enough negatives here. 3 of those oxygens are negative, and 2 of our aluminums are our positive ones. Actually, this does work because now we have a total of 6 negatives and we have a total of 6 positives. That's good. We can write out our chemical formula as Al2. That's how many aluminums we needed to scoop up. O3. That's how many oxygens we needed to scoop up. Notice here, when we write ionic compounds, we do not include the charges when we're writing that chemical formula. We know what the charges are, and so we don't have to write it. Step number 4 on this list is double check your subscripts here. Is there a common factor? Can you scale this recipe down to be more simple? For this problem, the answer is no, and so we're all set. This is all good. We can introduce a second strategy that's maybe a little bit faster. This second strategy we can call the subscript swap method. Our plan is just a simple math trick that allows us to very quickly get a charge neutral compound. The math trick is this. You take the charge that you have for your positive ion and turn that into the subscript for your negative ion. Likewise, you take the charge that you have for the negative ion and make that the subscript for your positive ion. This is a nice little math trick that allows you to get a neutral compound. Notice here, we're only taking the numbers in our charge, not the sign. It doesn't make sense to write -2 for our subscript because we can't have negative numbers of atoms. We do want to have 2 of these aluminums, even though there's a negative sign up here. Again, we have one last step. We want to double check our subscripts and make sure that we cannot simplify to a simpler ratio, simpler recipe. For Al2O3, we're all set. For Mg2O2, well, both of these can be divided by 2, and we can scale down to just Mg1O1, which really is better written as MgO. This swap method gets you to a neutral compound, but it does not always lead directly to the smallest whole ratio numbers. So we do always have to check there, do this last step as well. We have a third method, which is not going to be very convenient for this kind of problem, but it's nice to introduce because it will be helpful later on when we're trying to go backwards. But here we go. Our third method is to do some math, set up a little algebra problem. We can use that charge equation to figure out what the ratio has to be for our ions. Here's our example. We have calcium combining with chlorine. We know that there are some number of calciums and some number of chlorines. We can call this X and Y because we don't know what they are yet. We don't know the amounts. What we do know is the charge. Calcium is always +1, chlorine is always -1. We can build up our algebra equation by taking our charges and multiplying by those subscripts to figure out the total amount of positive charges and the total amount of negative charges. Once we solve this algebra problem, we get that ratio. In this case, we need twice as many chlorines compared to our calciums to get that nice neutral compound. Again, we can leave this method for now, but I did want to introduce it because we'll need to do this kind of math soon when we're starting to go backwards instead of forwards. We have some problems we can do as an example. If we're starting with strontium and chlorine. Strontium we know is the symbol Sr, and since it's in column 2, it has to have a charge of 2+. Chlorine is in group 17. It has to have a charge of -1. I'm going to do that first method I introduced just for fun. If we have a bunch of strontiums and a bunch of chlorines, can we find a group, a set, that leads to a neutral compound? If we grab one of our strontiums and one of our chlorines, this isn't going to cut it. 2 positives and 1 negative isn't good enough. So we're going to have to grab 2 of those chlorines. Now we have 2- from our 2 chlorines, and we have 2+ from our single strontium. SrCl2. Jumping down a couple problems, if we have calcium and bromine, again, we can figure out the charges that are present using the periodic table. Calcium 2 plus, bromine has a charge of -1. Let's do our second method this time. We can take that 2 plus, turn it into the subscript for our bromine. Let's take our -1, well, we'll take just the number 1, and turn that into the subscript for our calcium. What we get is calcium with a subscript of 1. Actually, we don't need to include that subscript. And we get bromine with a subscript of 2. Can we simplify this ratio any further? No, we can't, because we have a ratio of 1 to 2. That can't be any simpler. Finally, we can do our calcium and our sulfur example. Calcium has a charge of 2 plus. Sulfur has a charge of 2 minus. If you want to do that swap method, that's kind of fun. We can say that we have Ca2S2. Oh, careful. This can be simplified further. We can just write this as Ca1S1, or really just CaS. There are 2 more problems on this slide. Take a moment, grab some paper, and see if you can get that good answer. One final note here before we dip out. Our molecular compounds can also have their chemical formulas written, but they're not going to be nearly as predictable. Our molecular compounds are not combining based on their charges, so there's no way to predict exactly the ratio that's going to be required. This is just a sneak preview. We'll talk a lot more about our molecular compounds soon, so stay tuned for that. All right, we've made it to the end. We've been able to determine the correct chemical formulas for these ionic compounds, assuming that we know the charges on those ions. Well, there we go. Thanks so much for tuning in. Hope you all have a great day, and I will catch you next time.